First of all, my name is Alex Ainscow, and this is Bill Scales. We're going to be presenting the new Erasure Coding code together, new Fast EC, it's become known, in the Tentacle release. Do you want to say a few words before I begin, or should we just start? Okay. So, before we really can explain how we've made Erasure Coding faster, first of all, we have to explain what Erasure Coding is. I apologize if you already know what Erasure Coding is, but I'm going to go through it anyway, just to see if we can get a level set to where everybody is. And before we understand what Erasure Coding is, we need to understand what a replica is. So, a replica is essentially 3 copies of your data. So that's the simplest way, is each object is put sequentially on a disk maybe, or, and then we duplicate that data 3 ways. So this is a replica 3. So the storage efficiency is not great. You need to provide 3 times as much capacity as storage that's presented to the final user. So a much more efficient way of storing this data on the same 3 devices is to stripe that data across the devices. Now this is great, this is much less storage used. However, unfortunately we've now lost our data redundancy. We can't lose any of these without losing some objects. So what we do is we apply some clever maths, which I'm not going to go into here, and we come up with coding parities, or coding shards. And so we create a mathematical equation which takes A, B, and C and creates U and V. U is usually just an XOR of A, B, and C. V is much more complicated. But the properties of the maths work out that you can lose any one of these devices, or any 2 of these devices, in fact, and still recover your data, and your data never goes offline. I'm going to be talking a little bit about some values within Erasure Coding, specifically in Ceph. And there are these 2 values you may well have heard of. They're called K and M. K is the number of data shards, so that's the number of devices or OSDs that we stripe the data across. M is the number of coding shards that we provide, and you can lose up to M devices or M OSDs without losing access to your data. There is also an important dimension called the chunk size, and that is, or otherwise known as the stripe unit. I've got to apologize, internally in the code it's called a chunk size. To the user it's called a stripe unit. But they are exactly the same thing, and it's how much do we write to one OSD before moving on to the next. Okay. So, what is the performance like between replica? So we know Erasure Coding is much more efficient in the uses of space, but how does it compare to replica in terms of performance? And with legacy EC, so before we did fast EC, the replica was the best performance, and that's our benchmark of performance in Ceph. How close can we get to the replica code? But the overhead is 200%. Right? You have to create 3 copies of your data, so you have to provide an awful lot more storage, and that's very expensive. Erasure Coding, on the other hand, is much more efficient, but its performance isn't quite so good. And largely in legacy EC, it's acceptable for some applications. And that's, and the question of which applications and how do I make that decision is a long and involved one that I don't have time for here. Our aim with fast EC is to change one thing, and to change that we're going to get good performance from fast EC. Now, I would love to stand here and say we've blown replica out the water, but I just don't think that's physically possible. So the aim is to make it good enough for any application, and more cost effective. So we'll get into that in a bit. So, yeah, So that's the summary. Good enough for any application is the target for FastDC. So how do we do this? Well, first of all, I'm going to talk about how we improved read performance. So read's the slightly simpler one to understand. And to really understand it, you have to look at how the legacy EC implementation did what it did. And actually, I'm going to pause here 1 second. The legacy EC implementation is not a bad Erasure coding implementation. It's just been targeted at a specific use case. It's targeted at large object. And it does that very well. What we're doing with FastDC is to make it apply to the other applications like RBD and Ceph FS as well. So bearing that in mind kind of helps understand why some of these decisions were made. So read performance, the legacy EC, it will read an entire stripe no matter what data you're trying to read from it. And it will then throw away all but that one piece of data that you actually need. That's clearly a massive amplification of read. So it was quite one of the first things we wanted to do is reduce that down to just reading the data we actually need. Now we do amplify a bit. We align to 4K, and that gets you lots of memory efficiency and efficiency of the SSD. So that's actually a good thing to align to. To work around this legacy EC, they said the chunk size is always 4K. Or, sorry, the stripe unit is always 4K. And so this, you were still reading far too much because you still read an entire stripe, but by reading just a small subsection of a stripe, of a strip, we can improve our efficiency significantly. Also, the higher value of K you choose, which gives you higher data efficiency, the more data you have to read on every read, so the less performant your Erasure coding becomes. With the new EC, that scaling doesn't exist. You can choose any K value you like, and the read performance for small block reads is just the same. Secondly, we've actually improved the space efficiency as well, especially for small blocks. So what the old EC code did is it always padded out every shard to the same size, and what's in yellow here is wasted space. So the red object is what we actually need, and the coding shard or shards is what we need, and then we wasted all the yellow space. So FastDC for small object is now more efficient than old EC, and actually for the very small objects that are smaller than one chunk, they're actually the same efficiency as replica. You actually, the storage efficiency comes still in larger object, and we're going to talk at the end about how we can improve that further as well in the future. So with these two things together, we achieve a pretty remarkable performance improvement. Now I'm going to make a quick note on how you read these graphs. So these graphs show the latency against, so number of IOs we're trying to achieve and the latency we get from those IOs. A perfect curve here is not really a curve. A perfect curve would have a kick in it here, and it would be a kind of a corner, essentially. These are often called hockey stick curves. And the bit you're looking at is where this line goes vertical. Now, this is roughly, for very small reads, we can get roughly 3 times the read IOPS out of Erasure coding, out of the same hardware. And as block sizes start to get big, the gain we get actually gets smaller because we're actually reading entire blocks. And by the time we get to full, very large reads, there's still we still have managed to get a small performance gain. We've inspected the code quite a lot and found a few things to fix up. So when you're starting talking about large blocks, your gain is much smaller, but it's still a significant gain, I think. And the point to make, and if we move on, we've got to keep replica in mind here. Replica's not going anywhere yet. Replica's still going to be high performance on reads. But what you've got to look into here is that the cost saving you're getting and the scalability of Ceph. So while the reads are still at roughly half the performance of replica, we're doing it at just over a third of the cost. So there's some real savings to be made there by moving to a more Erasure-coded architecture. And as a bit of a preview, you might have seen all this before if you've watched some of our videos, but we've not talked about this before. So the project we are currently working on, this isn't going to be in Tentacle. We are aiming to put it in Umbrella. We are looking to, rather than, sorry, I'm going to start again. So the client currently sends a read request to what's called the primary OSD, so it picks one of the OSDs. That OSD then sends read requests to all of the other OSDs, which then reply to the primary. The primary puts together all of the data and then sends it back to the client. What we can do instead is make the client request data directly from each OSD and then reassemble the data in the client itself. And what we achieve then is parity with replica on read performance. And having gone and written this code, I know why. It's because I largely cut and pasted the code out of replica and put it in Erasure Coding. So it really shouldn't be a surprise that it's performed exactly the same way. But all the fast EC work we did makes this possible. There's a bit more complexity to it. Actually, as you get very, very large reads, the performance is actually better than replica in some cases. And in the middle, it's a bit worse. So there's a kind of complex relationship. So I also want to talk about overwrite improvements. Now, when we overwrite an object, what our aim is to take an object and just write a small part of it, okay? Now, again, back to what the legacy EC code was doing, and again, this makes sense for large objects where you probably very rarely actually overwrite them, is you read the entire stripe, you modify the bit of data you want to modify, and then you write back, you calculate the coding shards, and then you write the whole thing back. So we've done 3 reads, 4 writes, and as you grow the value of k, that gets even worse. So I've given an example for a 8 plus 2, so k equals 8, m equals 2. You do 8 reads and 8 reads and 10 writes. So let's go to what we're doing in UEC or fast EC. So we've got the same problem. We're going to overwrite a section. So fast EC will calculate the minimum amount of data that it needs to read. So it doesn't need to read the bit it's going to overwrite. Okay? It doesn't need to read the whole stripe. It will just calculate what it needs to read. It will then insert the new data and have a partial substripe of data that it can calculate the parity from. And then when we write back, we only write back the data that's actually changed. So the result is, in the basic case I've written here of 3 plus 1, we've done 2 reads and 2 writes. In an 8 plus 2, we've done 7 reads and 3 writes, which is a big improvement. But we can do better. So there's another scheme we've put in place called parity delta writes. Now, honestly, we didn't invent this. This is a technology that's applied to a lot of storage products, but we did apply it to Erasure coding in Ceph. So in a parity delta write, again, we start with the same problem. We want to overwrite a small section, but instead of reading the rest of the stripe, what we do is we go and read the data that we are changing, and we read the coding parity or coding shards that we have that we are going to change. We then take the new data and calculate the difference between the 2 values. Or calculate what's called a delta. In some cases, that's just an XOR. In some cases, that's a bit more complicated. But then can apply that delta to the parity, and then we can write that back. Okay? So what we've done there is to reduce the number of reads we have to do. Now, in the particular example I've shown you here, it's simplified so I can fit it on a PowerPoint presentation, and it's actually the same efficiency. For an 8+2, that's actually only 3 reads and only 3 writes. So that's a much more efficient way of going about read, modify, write. And what the code will do is every time it gets in a write, it will calculate what the most efficient mechanism it can use it on a per I/O basis. So each I/O will be done with the most efficient technique, and it will apply that technique. And in fact, it actually it takes into account previous reads and writes as well, and it looks at how much it's got available in cache and things like that. So it's always trying to optimize and minimize the number of reads it's having to do. So for 8+2, we've now got that down to 3 reads and 3 writes. So you wanted to take over for the performance result.
Okay, so here we've got the performance comparison of the old code and the new code. You can see we've got some quite decent improvements. Again, for the smaller block sizes, that's where we've got the largest gains. When you get to the much larger writes, very modest gain there, but still a little bit that we managed to eke out of the code. Here's a comparison to replica 3. So you can see that replica 3 is still a long way ahead. So with direct reads, we're going to get to parity with replica 3 on the read performance. You know, what can we do on the write performance in the future? So Erasure Coding has more complexity to it. It's got more overheads. It's essentially twice as complex as replica 3. So the kind of theoretical best we could get is 50% of the replica 3 performance. You can see we're not too bad on the 4Ks. You know, a little more optimization to do there. We can probably, you know, eke out another 10, 15% maybe. For some of the larger sizes, there's more work to do. So, you know, we've got further optimization work. We will get a few more gains. You're never going to get the same that we get with replica. This chart shows what happens as you scale the value of k. And with the old implementation of Erasure Coding, we had the rather unpleasant property that as you increased k, performance actually got worse. And of course, you know, the bigger the value of k, the more storage efficiency you get. So you want as big a value of k as you can choose, but you know, you don't want that to happen with the performance. With the fast EC, the performance is pretty much the same regardless of the choice of k. There's a bit of variation there. We've only gone up to k equals 6. If you increase k further, it's going to stay pretty much within where those 3 lines are. So, you know, the message to take away is with the fast EC, choose the value of k to get, you know, the best storage efficiency. That's probably based on how many nodes you have in your Ceph cluster, as opposed to worrying about the performance impact of choosing different values of k. Another thing we're changing with the fast EC is the choice of the chunk size of the stripe unit. So with the old code, the default stripe size was 4K. You could override that and change it, though you know, there were some pretty unpleasant side effects of doing that. So, you know, in particular cases, it worked nicely. In other cases, it, you know, used an awful lot of capacity. With the new code, because we're not padding objects, because we're much more efficient in just reading and writing the bit of data being changed, a larger chunk size is better. We don't really want to break up small I/Os. So if you're, you know, reading 1632K, there's no point splitting that up and issuing it to 2 hard disks or 2 NVMe devices. It's much more efficient just to issue the whole request to 1 device. If you get to megabyte-sized I/Os, you know, at that point, it probably is worth, you know, trying to chop that up and issue parts to different drives, because then obviously they can process the request in parallel, and so you're going to get better latency, and you're going to spread your workload better across all of your devices. So, yeah, we can support a larger stripe size. This shows what happened with the old code if you change the stripe size and you were trying to store smaller sized objects. And so you can see the kind of inflation of choosing a 16K or a 64K chunk size is you could actually end up using 8 times as much storage to store small objects. With the new code, where we're not doing the padding, the increase is much less, and so larger chunk size is much less of a problem with the new code. This chart's a little more complicated. So in red, we've got the old Erasure coding with a 4K chunk size. In blue, we've got the fast EC code with a 4K chunk size. And in yellow, we've got the fast EC, and we've increased to a 16K default chunk size. At the bottom, we've got different Erasure code configurations. So we're changing the value of K, and so we've got 2 plus 1, 4 plus 1, and 6 plus 1. And then we're looking at what happens if you store different size objects. So the left-hand column is objects 0 to 64K. So, fairly small sized objects, and we're comparing how much capacity gets used for these different implementations. And so you can see 0 to 64K, if we keep the chunk size at 4K, we're about 4% more efficient in terms of capacity. If you go to a 16K chunk size, we're 1% or 2 worse. Second set of columns is looking at objects 0 to 256K. Third column is looking at 0 to a megabyte. You can see that by the time we get to the larger sized objects, the choice of chunk size is really having a fairly insignificant effect on capacity usage. But if you're storing small objects, and we know some people are storing billions of small metadata objects, then this can make a difference. As we increase the value of K, the storage savings become better. And so we can see if we go to a 6 plus 1, for example, stick with the 4K chunk size, and you're storing small objects, you can actually be 20% more efficient in terms of storage. Even if you go for the 16K chunk size, still more efficient than the old code. And so our recommendation is use a 16K chunk size with fast EC. There may be some applications and use cases where you can increase it further, and increasing it further will improve performance. Increasing it above 256K probably isn't going to make much difference. But if you're storing very large objects, if you're using RBD, then maybe there's a use case that says you get a little more performance with 128K. If you just don't want any hassle, you don't need to tune that last % or 2 of performance out of your system, go with 16K. It's going to be good enough for what you need. Backfill recovery performance. Always a problem for your systems. It's not the kind of good path case of the system where performance problems show up. It's when the system's recovering from a failure, that's when you're putting the extra strain as it's rebuilding that data, and that's where you're going to see performance issues. Moving data around as you split or merge placement groups to kind of increase or decrease the number of placement groups, or rebalancing data. You've added new storage to your system, you want to spread it out across the new storage. All of that's involving moving data around. We've made several efficiency improvements there with the new fast EC code, really minimizing the amount of data that we have to read and write to do those rebuilds. Looking a bit ahead in the future, so Alex has already talked about the direct reads, so that's on track to come out in the umbrella release next year. We're looking at packing small objects. So if we write very small objects, then today we essentially end up with the storage efficiency of replica 3 because we end up with one data shard and the coding parities to go with it. If we pack lots of small objects into one bigger object, then we can actually improve the storage efficiency. If we do this, then we can also increase the default chunk size further, and so we're kind of thinking about, can we get to that 128K, 256K default chunk size without having any impact at all on storage efficiency. We also know if you have billions of very small objects in a Ceph cluster, that backfill and recovery performance can come an issue. Essentially, it's recovering each one of those small objects one at a time. Doing this kind of packing and coalescing objects together will help improve backfill and recovery performance as well. Talked about direct reads. Pool migration. One of the things we noticed today is if you add extra nodes to your cluster, you can't go and change that Erasure code profile. You've chosen a value of K based on the size of the cluster that you started with. You've gone and added some extra servers. Wouldn't it be nice if you could increase the value of K? So we thought about ways of doing it, and we decided what we're going to implement is a way of doing a pool migration. So you can migrate all of the objects from one pool to another pool completely non-disruptively. So obviously we've got to move the data, and so it's going to be a bit like a backfill in that there'll be some overhead of doing the copy, but we're going to do that migration whilst I/O continues. There's going to be no outage, no reconfiguration, not even a little glitch at the start or the end of the process, all completely online. And that's going to be a way of allowing you to adjust the Erasure coding profile. So if you want to change K or you want to increase the chunk size, you'll be able to do that non-disruptively. We want to make Erasure coded pools have all of the functionality that replica pools have. And so today they don't support OMAPs, they don't support classes. We're going to add that support. When you're using RBD with Erasure coding, you have to kind of create a replica pool and an Erasure coded pool. That's a bit of a faff. You've got to remember to specify both pools every time you create an image. Our aim is to get rid of that and get to the point where you can have just an Erasure coded pool and just create images in the Erasure coded pool. So kind of simplify the behavior. Why is that important? We want you to be able to use pool migration to migrate a replica pool and turn it into an Erasure coded pool. And so, if we had to add a second pool into the equation as we did that, that would have made the pool migration more complicated. If we can get it so that you can just have one pool for Erasure coding, then you can take your replica pool, convert it into an Erasure coded pool. A few more things we're looking at. Stretch clusters today typically use replica at each site. We're looking at, can we support Erasure code stretched across sites, and that's either kind of one Erasure code pool stretched across two sites with kind of understanding that reading data locally is more efficient than reading data from the remote site, but also having an Erasure coded pool where you have, say, a 3+1 at site 1 and a 3+1 at site 2, and so it's like two replicas of an Erasure coded configuration, one at each site. Okay, thank you. Any questions? Yes?
Is this a different on this format, so it would require a new pool to be created, or is some existing pools with data can convert into this new image?
Okay, so good question. Have we changed the on-disk format of the data, and can you switch from the old format to the new format? So yes, we have changed the format of the data structures stored on the OSDs. The new code understands both the old format and the new format, and so we can take an existing pool. There's a new flag you set to enable the optimizations on the pool. That enables the new code. So we've actually kept the old Erasure code, added the new Erasure code, so you can upgrade to the Tentacle release. You're still running the old Erasure code, nothing's changed. You can kind of test out a new pool with the FastEC, get happy with it. Then when you're confident, you can set the flag to convert your existing pool to use the new FastEC and get all of the performance benefits. Because it does change the on-disk format, once you've kind of done that switch, you can't switch back again. Do you need to upgrade everything? You have to update the OSDs and the monitors. You don't have to update all of the clients. So if you've got kernel clients or clients that you don't want to upgrade, or not going to upgrade immediately, you don't have to upgrade the clients to take advantage of all of these new performance improvements. Yes?
I noticed in most of your graphs it was IOPS rather than raw throughput from a bandwidth perspective.
Right.
Do you see a lot better bandwidth throughput as well, and how does it compare to the rest?
Okay, so the question was, a lot of the graphs were showing IOPS improvements, what's happening to the bandwidth, the megabytes per second numbers. So the FastEC changes are kind of primarily focused for file and block usage, where number of IOs per second is probably the most important performance metric. But there are workloads that are bandwidth concerned. Those are much more like the S3 object workloads. So they typically have much larger IO sizes. The performance improvements there are much more modest. So think 5 to 10% performance improvement. So if you're an S3 object user and you turn on the FastEC, you'll get that kind of performance improvement for your large objects. If you've got a mixture of large 100 megabyte plus objects, but also smaller objects, then you're going to get the performance improvement for the smaller objects. If you have objects with indexes in them, and those indexes are being accessed to actually locate which part of the object to be read, then those random access reads to get parts of the index, those are going to see the performance improvement. Yes?
Have you observed any noticeable impact, either positive or negative, on the CPU or memory utilization with switching to FastEC?
So the question was, has there been any impact on CPU or memory utilization? So shouldn't be any difference in terms of memory. The purpose of these changes is really to reduce the amount of I/O we're doing, and so we're looking at can we reduce the number of requests we're making to the HDDs or the NVMe drives. A consequence of doing less I/O requests is we use less CPU. And so the reason we're actually getting these performance improvements is that we've reduced the amount of CPU and the amount of storage overheads per I/O request. We do reduce the amount of network bandwidth, in particular between the OSDs as well. So if your network is actually the bottleneck, then even there we're helping a bit. Yes?
For your pool migration, is there any plans for that to be supported in Ceph as well?
So the question is, where are we going to support pool migration? So the pool migration is going to be a RADOS implemented feature. And so whether you're using RBD or you're using Ceph or you're using RGW, we'll support it and we'll be able to move your data to a new pool.
As a follow-up to that, migration is happening, would that be exposed in the extended attributes of files? Would you see that your files have moved to a new pool during the migration?
No.
No? Okay.
So as far as the kind of clients are concerned, they're still accessing the same pool that they were previously.
Okay.
It's just that we've kind of moved the pool and we end up leaving a kind of redirect stub
Got it.
marker in place. That's how we do it completely non-disruptively.
We're at 11:48, so
Yep.
we're 8 minutes over.
Okay. Yeah.
My question kind of followed up on his, was what kind of timelines do we see for the conversion to complete? Like, is it something that just happens in the background, we just don't know, or? Like,
It's going to be a background task. It's going to be similar kind of performance to backfill. And just like backfill, you have some knobs you can choose to say how fast it's going to occur. You've obviously got to get the balance right.
would it, like, if you do like a Ceph -S, for example, would
Yep.
it tell you like, I'm backfilling, doing the fast conversion, or is it just going to say, yeah, backfilling regardless?
So the pool migration will be, it will say it's migrating and same kind of estimates.
Just to
Okay.
clarify one thing on that. There's no migration when you enable FastDC. Full migration there is for changing K and translation of that. The FastDC conversion is instantaneous.
Okay, right, thank you. I'll have to stop here.